So let's now talk about how do you actually aggregate test scores, because this is the entity that we're then going to standardize, right? So the most standard thing people do is just take the fraction of the percentage score on an actual test, okay? So if you get 13 out of 25, that's a raw score of 52%, and then you will take that, subtract the mean, and divide by the standard deviation to come up with the standardized score, okay? Now the other way to do this is to use item response theory, and this is considered a better way to do this, and I'll tell you why, okay? So when you take a standardized raw score, while this is quite common, these do have several limitations. So the first thing is that the student's performance on these tests will usually be measured with a fair bit of error because there's very few items. A more subtle point is that items of moderate difficulty will usually give you more information about the student learning than items that are too easy, which everybody gets right, or too difficult that everybody gets wrong, okay? So whereas when you take the raw score, you're weighting all of these items equally, whereas they actually don't have equal information about the student's underlying kind of learning levels. So it's also more difficult to compare across subjects or over time, because this percentage score or raw score is in some ways a very not a very useful number, because if the test is very difficult, the percentage score could be low. If the test is very easy, it could be high. So if I say, oh, a kid's test improved from 38% to 42%, from going from grade 3 to grade 4, that tells me nothing about the learning level, because the grade 4 test is going to cover a different set of subjects and topics. Or conversely, if a kid gets 50% in grade 3 and 45% in grade 4, that does not mean that the learning level has gone down, right? Because the construct of the test could be completely different, okay? So what item response theory does is it's a statistical tool that has been widely used across assessments around the world, and this is used by the ETS as for the SAT, for the GMAT, and there's a whole body of research underlying the use of item response theory. The main thing it does is that it allows you to compare kids on a common distribution so that you're able to do better cross-sectional comparison and better over time comparison, even though the content of the test itself might be changing, okay? And the basic idea of IRT is that it models the probability that an individual with a given underlying ability, where ability is a measure of your kind of current learning level, okay? So let's say there is one latent factor that you can collapse a student's underlying learning level into one dimension, okay? Now the idea of IRT is that you can then use that and the properties of individual questions to then predict the probability that a student will get that question correct, okay? So what IRT does is it looks at all the answers to all the questions that students have put together and then uses that jointly to estimate a maximum likelihood model to say what is the underlying ability level that is most likely to have generated this particular pattern of answers that we observe, okay? So there's a very nice paper on this by Jishnu Das and Tristan Zayonk, which I highly recommend for those of you who want to know more about the properties of IRT and how it helps, okay? But the most important advantage of IRT is this allowing the ability to link across and over time. So let me kind of make this more concrete with the core idea, which is that of an item characteristic curve, okay? So what you have on the x-axis is this measure of ability. And the curve is the property of a specific question, okay? So every question that is in an IRT model this is what's called a 3-parameter IRT model, has 3 pieces to it, okay? There's what's called, there's the guessing parameter, which is what you see on that horizontal dotted line there, so that's CG. So what that tells you is that even a kid with almost 0 learning level can get this question right, say 20% of the time. So suppose your question is a multiple choice where it's 1 in 5 and you could know nothing and still have a 20% chance of getting that question right, okay? So that captures what's the guessing parameter, which is if you look at how that curve goes, it's that even if your learning level or ability is like -3, you would still have a C percentage chance of getting that right, okay? Now, if you look at the curve, there's 2 other pieces that will show up. there's this guy called the difficulty, and that in this graph is BG. And the difficulty is defined as the level at which the probability of getting the question right is halfway between the guessing parameter and 1. Okay, so, and what that tells you is a student at this ability will have a 50% chance, a 50% non-random chance, right? Like, I mean, taking out the guessing of getting the question right, okay? And so if you're above that ability, you're more likely to get it right. If you're below that ability, you're less likely to get it right. And then the third piece of this is what's called the discrimination parameter, which is the slope of that item characteristic curve at the point of difficulty, okay? And so the way to think about this is that a question with high discrimination is a good question because it tells you that kids above this will almost always get this question right, and the kids below this level of ability will almost always get it wrong, okay? Whereas if this ICC is much flatter, then that tells you that even kids who don't know much could get it right, and kids who know a lot could get it wrong, okay? So a good test will consist of a series of items that have a range of difficulty ranging all the way on the scale from say -3 to +3, but with each of these questions being high discrimination questions, and then a test that has that set of individual items will have the best precision in terms of measuring the precise level of student learning. Okay, so you can read much more about this in that paper by Das and Zayonk, and the good news for you in practice is that they have made this very easy to implement. So Tristan, like Neen, has created code in Stata and a program called OpenIRT that you can use to implement this. Okay.